Today we are starting 9.3. We're looking at more log equations. Before we get into the equations, there is an important concept we need to discuss, and it's best seen by looking at the graph of a log. So all log graphs essentially look like this, give or take. And the curve, just so you can clearly see what we're looking at here, it does appear to go practically straight down as it gets to the y-axis. That is what it's doing. For those of you concerned, we will not be graphing these in this unit. I'm going to throw out an old vocab word, something we used a lot last semester, and that word is domain. We call it domain and range, but today I just care about domain. Now when I ask what is the domain, what part of the graph are we looking at to answer the question? Left to right. We're looking at the x values. So the domain is asking for the included x values. Now that there's been some time since you've last done this, I'm sure several of you have picked up the bad habit of anytime you see the word domain, you associate it with the answer negative infinity to positive infinity. That is true for a lot of graphs, but there are also a lot of graphs that it's not true for, and this is one of them. So if that's where you're at, that's wrong. That's not how we do domain. So domain, we check left to right on the graph to see which x's are included and which ones are not. So looking at the left side of the graph, what is the first number that is included? The far left number. Nope. By the graph, not the like image. The curve here. 0. 0 appears to be where it's starting, the y-axis. That's as far left as it goes. Something that might help a little bit is knowing that there is an asymptote here on the y-axis. That is what is preventing that curve from moving more to the left. That's what's stopping it in its tracks. Because it's an asymptote, technically we are starting at 0, but that 0 is not included in the domain. When something's not included, we use a parenthesis. And as we move to the right, where is the graph heading? To infinity. To positive infinity. And infinities always get to which grouping symbol?
Parentheses.
Got to be parentheses.
Wait, what gives brackets the numbers?
Yeah.
Numbers that are included, and since 0 is not included, it didn't get a bracket this time. But usually numbers get brackets, yes. Infinities always get parentheses because infinities aren't real numbers. They basically represent higher than we can understand or comprehend. You can't put a bound on infinity. All right, the big point that I'm building to here. What numbers are not included in the domain? What type of numbers?
Negative numbers.
The negatives. Everything to the left of that asymptote are the negative numbers. So no negatives is the big point here. So the main takeaway, you can't, absolutely cannot, plug negative numbers into a log. Hopefully that's clear on the graph why you can't use the negatives. It's not even within the domain. It's just not part of the graph. But we will get into calculator stuff later just to kind of give you a little Hint of what that's going to look like. If you try to put a negative number into a log in your calculator, it will say domain error. And that's exactly what I just showed you here. Domain error, it's not in the domain of the function. You can't do that. So if you ever try, that's what's going to happen. We'll come back to that point later. For now, let's look at some equations to solve. Number 1, log base 4 of x equals 5 halves. There are going to be a few different types of log equations throughout the unit, so we like to get into the habit of labeling them and identifying them early on to be able to tell them all apart, because each type is solved a different way. You could actually solve this based on Tuesday's notes. This is very similar to what we've already been doing. This is the type that we call log equals number. I would like to clarify, it's more so the fact that we have one log on one side and then the other side is not a log, it's something else. Usually a number, sometimes it could be another x, sometimes it could be a whole expression, but just the fact that you have one log and that's it. That's what's important. So whenever you have log equals number, the way to solve is you switch the form and solve. That's the way, that's the approach. Which is what we did in Tuesday's notes. So we are in log form currently, and we're switching to the other form, exponential form. Base stays base, the other two switcheroo. My base here is 4, big 4. The other two switcheroo. This is exponential, so the next thing is the exponent, 5 over 2. Equals, and then the x goes on the other side. Switch the form, check, solve. What are we solving for again? X. Is x by itself? So is x solved for? Yes. X is solved for. 4 to the 5 halves. You can type that into your calculator. So let's talk about it. Our base is 4. And then the universal exponent button, the caret. When you type a fraction in as your exponent, it is super duper important that you use parentheses. Some calculators are pickier than others about this. So when in doubt, use parentheses. 5, and then for your division, you can either use ABC or the division symbol. They both work. I'm going to use ABC. Close off the parentheses, and you get 32. 32 is equal to x. And there you have it. I'm going to write down the buttons I pressed, just write them out as a step in case anyone wants to write that down for later. So in the calculator, I typed 4 and then the caret, parentheses 5. Now I'm going to use division here because I feel like if I wrote that down, some people may not understand what it means for the ABC symbol. So 5 divided by 2 will work. Or you can use the ABC symbol, of course. As you can see, some problems are going to be very straightforward, very quick and easy. Others are going to take more steps. Questions over number 1. Number 2, similar type of problem. It's just going to require a few more steps. Once again, we have a log equals number set up here. And when we have log equals number, we switch the form and solve. So we're going to take the same approach. We have a log currently, and we need to switch it to an exponential. Base stays base. My base here is 2. The other 2, switcheroo. So 3 is the exponent, and 2x goes on the other side of the equal sign. Here's where some students may overthink and get confused. I want to show you the distinction. This is what we were doing, and this is what we are doing now. The difference on the post-it note, this guy has the x as the exponent, so that's where you have to have the same base to solve. Here, this is just a regular 2x, no exponent. So we're not going to take the same approach that we've been using at all. Instead, we don't have to care about matching bases here. Let's turn 2 cubed into what it's actually equal to. What is 2 cubed? 8. So turn it into just 8 equals 2x, and then you have an equation. Solve it. Divide both sides by 2. 8 divided by 2 is 4. X is 4. Questions on number 2? Number 3, I'm just kicking it up just a small notch. Log of 4x plus 2 minus 5 equals negative 3. Now, I wouldn't call this log equals number yet because our log is not by itself. Whenever a log has multiple things in it, as you see right here, they'll indicate that with parentheses. So this whole thing right here is the log. It needs to be just the log equals number, and we're not there yet. We have to move the 5. So actually, our very first step here is isolate the log. If you switch the form right out of the gate, your answer will absolutely be incorrect. So it's important to isolate it first. Get it by itself. So we have minus 5. Let's add 5 to both sides. We have log of 4x plus 2 equals negative 3 plus 5 is 2. And now we have log equals number. And when you have log equals number, you switch form and solve. We are currently in log form, and we need exponential form. Base stays base. What is my base? Yes. So if you remember, there is a small blip about this in Tuesday's notes. I said it wasn't going to be in those notes, but it will be coming up. Here you have it. The common log, when there is no base, it's blank. The assumed number is 2. 10. I don't know why I said 2. 10. The assumed number is 10. So my base here is 10. And then the other 2 switcheroo. Exponential form, my exponent is now the 2. Equals, and yes, you can move this entire thing to the other side. So sometimes you'll have multiple terms there. Just follow the rule and you'll be fine. And then we have the same thing going on as the previous problem. We have a number squared on one side, and then the other side is just an expression to solve. So we'll turn 10 squared into what it's actually equal to, 100. 100 equals 4x plus 2. And then we solve. First we'll move the 2. It's a positive 2, so minus 2 minus 2. 100 minus 2 is 98 equals 4x. And then we need to remove 4, so divided by 4, divided by 4. X equals, and that will reduce, so I'll reduce with my calculator. 98, ABC 4, and I get a mixed number at first, remember it's second ABC to flip it to an improper, which is how I want the answer. 49 over 2.
Please pardon interruption. For some reason,
So our answer is 49 over 2. Questions over number 3 before we look at the other type of equation in these notes. Number 4. Log base 3 of x plus 17 equals log base 3 of 3x plus 23. This is the type, this is pretty easy to follow, log equals log. You have a log on the left, and a log on the right. Just one though. That'll come up later. When you have log equals log, I'm sure some of you already have a hunch. Yes, you will approach it the same way we approach this. When you have the same base, you can drop and then focus on the exponents. We'll do the exact same thing. We have the same log on both sides. They will always be the same log. If they're different, you actually can't solve it. Same log, drop, and solve with what is remaining. So that's going to be the first step. Drop the logs. We have x plus 17 equals 3x plus 23. And then we solve like normal. I have two x's, x and 3x. They're on opposite sides of this line. We can't combine. Let's move the smaller one, which is 1x. Positive 1x, so I will subtract 1x on both sides. We get 17 equals 3 minus 1, 2x plus 23. 2 steps to solve. Need to move over that 23 first. It's positive, so minus 23 on both sides. 17 minus 23 is 6, negative 6, equals 2x. And lastly, divide off the 2 on both sides. Negative 6 over 2 is negative 3. And let me catch up on my steps over here. Drop the logs, solve. There is a catch. While this is a lot more straightforward to solve than the previous problems, dropping the logs, there's an issue with it. So I'm going to flip back to the front side real quick. This rule here, you can't plug negative numbers into a log. So having a log in your equation is putting this restriction on what the answers can possibly be. And when you take the logs out, like they weren't even there to begin with, you're removing that boundary and that restriction. And now answers, extraneous answers, we talked about that last unit, can come out that shouldn't have worked to begin with. So when you drop the logs, you must check your answer. And that only happens with the log equals log problems. That's the only time you are required to check your answer. So whenever you have log equals log, check. We will check our answer, which is x equals negative 3. So I'm going to plug negative 3 into the x's in my original equation. Log base 3, parenthesis, we have x, which is negative 3, plus 17, equals log base 3 of 3 times x, which is negative 3, plus 23. Now, I'm not going to put the logs into the calculator. That's not the important part. What's in parentheses, that's important. So I'm going to go ahead and set this up. Log base 3 on both sides. And then we'll get the number in parentheses to compare. Left side, we have negative 3 plus 17. we get 14. Right side, we have 3 times negative 3 plus 23. 14. This tells me a couple things. Number one, I got the same number. That means I did my math correctly. Number two, and this is what we're checking for. We got a positive number inside of those parentheses. That's what we want. That is what's going to pass the check. So our answer, x equals negative 3, is legitimate. It's okay for your x value to be negative. It's not okay for the overall number, once you plug it back in, to be negative. There is the difference there. Questions on number 4 before we do one more of those? Yes? If these turn out to be negative, then our answer doesn't work. I'll get to that in a moment. Number 5. Log base 2 of x minus 4 equals log base 2 of 3x. So as you can see here, we have a log on the left and the right. This is log equals log. When we have log equals log, the process is drop, solve, check. Three steps, drop, solve, check. So first we drop the logs. We have x minus 4 is equal to 3x. Again, reminder, you have two x terms. They're on opposite sides of this line. Do not move the 3x. It's by itself. Leave it over there. Move the 1x instead. It's positive 1, so minus 1x on both sides. We have negative 4 equals 3 minus 1 gives us 2x. Remove the 2 from x, divide by 2. Negative 4 over 2 is negative 2 is x. We have our answer, but we must check. We are checking the answer, x equals negative 2, and put it back in the original equation. Log base 2 of x is negative 2 minus 4 equals log base 2 of 3 times x, which is negative 2. And then we need to get both of those numbers. Log base 2, log base 2. I'm not going to use a calculator for this. I'll just talk through the calculation. Negative 2 minus 4, negative 6. 3 times negative 2, negative 6. There's good news and bad news. Good news, I got the same number on both sides, so my math is absolutely correct. It wasn't a me issue. This worked. The bad news is they're both negatives. This is what we don't want. This means that our answer, x equals negative 2, is not valid. Therefore, our answer is what? No solution, exactly. If it fails the check, then that's it. No solution. So hopefully you can see why the check is extremely important. If you don't do it, you would have no idea that your answer is actually no solution.